There's a lot of hype about yet another seemingly imminent asteroid impact. But how close are we really to getting hit by asteroid 2024 YR4 on December 21st, 2032? Wow, that's a lot of numbers and letters. Also, when can we see several planets in the night sky all at once? When is our next visible lunar eclipse, and what is the significance of our MA2 Mercury Capsule? So glad y'all asked. Welcome to the HMNS Beyond Bones podcast. I'm your mental curator, Johnny Hemberger. To help answer all of these questions and more, I am joined by a true pioneer and an absolute American hero, HMNS's own Curator of Astronomy, Dr. Carolyn Sumners. While her illustrious career includes training astronauts during the golden era of American spaceflight, she graciously gives us her time today. And what better way to kick things off than your humble host getting hit by a real asteroid?
Hold out your hand. You have now been hit by a meteor.
I won't tell OSHA that you hit me with a meteor on the job.
That's an iron, and you can see that as part of the Hemberger meteor crater, meteor.
Yeah.
You can see it would be easy to deflect such a meteor.
And all these little, how it looks and how it's shaped is how it tumbled and got eroded
That's
as it went through the atmosphere.
Pitting it, so to speak.
That's so cool.
But a meteor can also, an asteroid can also be, I guess a gravel pile is a good way of saying it. And that's a much harder asteroid to move. So we've been talking about moving asteroids. If an asteroid was coming close enough and we thought we ought to move it, the only downside is we don't want to move it into our orbit by accident. So we are learning how to do that, and after all, we'll just tell Elon Musk to move it.
put Elon on it. So I think that's probably a good place to start. Now that you've hit me with an asteroid, and I'm one of the few people in the world that can say I've been hit with an asteroid, tell us about the probability of, is it YR 2024?
Yes.
Is that the one that's been discovered? That's all the hype in the media right now about the percentages going up and down and fluctuating up. It's hitting us in 2032. Can we talk about that for a little bit? And it was
discovered in December. That's why it's a recent discovery for us as we talk about it now. Mm-hmm. And they pretty much are saying, no, it can't hit us.
Right.
That it's just, you have to think about how far away these asteroids are, beyond the orbit of the Earth now. And we have to figure out how it's moving with this teeny bit of data. You get it off by a percentage point, a tiny percentage point, and it misses the Earth. Mm-hmm. Because you were talking about a hit in 2032, and that's a decent time in the future as well. So this is very tricky stuff to predict. We supposedly, unless something shows up that we weren't expecting, we've categorized all the stuff that's big enough to cause real damage to the Earth. And we continually watch it. The part of the challenge of figuring out where it's going is we don't know exactly what it's made and not exactly sure of all the data about it. And we're not exactly sure of exactly how close it might get to Jupiter or get to Mars or get to another heavenly body. So we don't know how it might be perturbed if we're waiting 5 or 10 years before it hits.
Right.
For instance, the big story about 10 years ago was Apophis. Asteroid named Apophis. That's just marvelous.
Yeah.
And we thought it could hit us. And it had 2 chances. And after study, we now know it can't hit us for 100 years. It's not going to, the next 100 years are safe for this particular asteroid. But we continually have to do that because they're small as far as compared to Earth.
Right.
But they're going fast, and if they hit, they can wipe out a city, for instance. Right. If it's as big as a football field, it can wipe out a city.
Right. YR 2024, that's what they're saying, is it's a city. The destruction is citywide.
Yeah, but it's got to hit the city. So it's not only got to hit the Earth, it's got to hit, you can't fall in the ocean, that will get a tsunami or so, but that won't hit the city. It's the real damage does if it hits land.
And I was looking it up, first of all, we get hit by asteroids all the time. They go in the ocean, they don't cause any damage. We're constantly pelted with small stuff from outer space.
Microwave-sized stuff and smaller.
Right. So that's just a cool note that we technically a whole lot of space material does reach Earth every
We're
year.
always
Tons
collecting
and tons
it,
and tons
and we're
of
shedding
it.
some. So.
Right, but it's not all the time that you detect one that can level a city. I was looking, it came across my feed somewhere. Well, what cities, if it had 100% chance of hitting the Earth, what cities would be in the crosshairs? And it looked like the United States was safe. It was more.
It's Southern Hemisphere.
Right. So I was going to say it looked like it was below the equator, and
Right.
I saw some cities in India and across Africa and things like that that might potentially, theoretically
Well,
be.
you hit anywhere in India and you've got a problem.
Yeah.
Because there's so many people who live in India.
I want to say it's well over 1 billion
Yeah.
people. I don't want to quote off the top of my head what I don't know yet. But so what are the percentages right now as of recording in February of 2025? What do we think at the moment?
Less than 1%.
Less than 1%.
In fact, I think they're pretty well at the point of saying it's not going to hit us. The only thing left is that we could hit the moon.
Right.
The trajectory says it might graze the moon, but the chance of the moon itself getting hit by this same asteroid is about 1%.
Right, and we saw in a simulation that I'll pepper in here as we're talking. We were as the simulation can change as more data is collected, but by right now, I'll show the simulation. It goes pretty wide past the Earth. It comes within the moon's orbit of the Earth, if I remember right from the simulation.
Apophis will do that too, and so we get to study it.
Right.
There's no doubt we get good eyes on it, and that always is helpful.
Some drive-by science.
Right. And but looking at all the rocks we know were there. Now, what we don't know is the comets, and because they're coming from far out. Now, they're very unlikely for a comet to appear, but we're not monitoring comets, except for maybe the closest ones that are in orbits that we can trace, like Halley's Comet. But the other comets that come from the outer solar, from way beyond Pluto, they're not there until they show up. If you remember, we had a comet you could see in the daytime in Houston, Hale-Bopp.
1997.
Yes, and that comet, if it hit us, could really cause mass extinction.
Yeah.
Because even though a comet is less dense, but it's traveling a lot faster. So you can usually take the size, the width of the comet, or the width of the asteroid, with the comet nucleus, to get a feeling for how much damage it can do.
So the comet, even though it could be less dense, theoretically it could contain more mass, I guess. Am I off base on there?
The mass, the density will be less.
Yeah.
So in a way, if you use the diameter of the object as your measurement, it's as big as a football field. It's as big as a microwave, whatever you use, and you have a number for it, of course. That's a pretty good measure for both comets and asteroids, because the asteroid is denser, so there's more mass there, but the comet is traveling so much faster.
Yeah.
And the energy you get, which is what causes the problem, is MC squared.
Yep.
So, you're squaring the speed. So the speed is really important here. And when it hits in another object, you have to dissipate the energy. And that's what causes all the destruction. That the object is moving fast and suddenly it's not moving at all. Well, that's a lot of kinetic energy that had to go somewhere. And it's gone into heat, into particulate material going up into the air, into digging out the hole. All those things are adding together, and that's why you have the big explosion. And that's why it pretty much isn't a glancing crater. If it's getting to count it all, the thing's going to explode when it hits, because suddenly there's all that energy to get rid of. And one way also to get rid of it is to explode it. When you hit the Earth, you damage the atmosphere significantly. And that's why an impact on the Earth probably does more damage, because we have an atmosphere. It won't slow it down, but it'll absorb all the mess that comes out of it when the asteroid hits.
We had it's not the same thing as an asteroid, but in some ways it could be relatable, I guess. The Tunguska, or the volcano that erupted under the ocean a few years ago. And it didn't cause global, summer, winters, and things like that, but it did put a measurable amount. I heard scientists talking about a measurable amount of water vapor now is up in the atmosphere because of that massive eruption. Do you remember that? They saw it from space, and the satellite imagery, poof. It wasn't an extinction level thing, obviously, but they could measure, the levels of these particulates in the atmosphere are because of that eruption.
Yeah.
So if an asteroid or a comet hits the Earth, and depending where it hits, the ocean or land or whatever, it's going to toss all that stuff. Like you said, the energy has to go somewhere.
Well, and what you have that causes the greatest damage in a way to life is the stuff that goes into the atmosphere.
Right.
Because what does it do? It blocks the sun. And what happens then? The plants don't grow. And when the plants don't grow, the animals that depend on the plants don't have food. Then the animals that depend on the animals that depend on the plant don't have food either.
Right.
So if you shut down photosynthesis with an impact with what you do to the atmosphere, that probably causes most of the damage, and that is damage that goes worldwide.
When people, I think maybe, if you don't think about it too much, you think the asteroid impact that killed the dinosaurs, they all died in a big fireball.
No, it didn't
instantly.
Hit them.
Right.
It destroyed their atmosphere.
It destroyed them. It completely obliterated the food chain. And that is what ultimately led to the extinction of not just dinosaurs, but a lot of.
But if you look at the data, because I was up in South Dakota looking at fossils one time, and I realized that the turtles had no problem.
Yeah.
The turtles just went right straight on through.
Right.
They didn't even notice.
Most turtles and crocs and alligators and things like that.
But I mean, turtles can eat anything, and so you had to be able to eat dead stuff because there's going to be a lot of that. You had not to depend. You're very slow moving, so you don't depend on a lot of oxygen in the air. As I say, you don't have to eat fresh fruit and fresh vegetables. You can eat dying things next door. So the turtles, unlike the dinosaurs who are very specialized and all, could not adapt.
Right.
But the less specialized an animal is, the more likely is it just goes right on through an extinction.
That's one reason I've heard paleontologists mention that it gives credence to the theory that dinosaurs were warm-blooded. They had to eat they had to eat more constantly versus a crocodile. A crocodile can go months without a meal. And that's and slow down. It's not hibernation. I forget what it's called. Rumination, something like that, where they go dormant in icy water with their snouts sticking out through the ice, and they can just basically chill there for extreme lengths of time while they wait for things to literally thaw out, and then they can hunt again for food. And cold-blooded animals like the croc can do that, which helps in an extinction event. When you don't, a warm-blooded animal needs to eat pretty often versus cold-blooded.
And cares a lot more about the temperature.
Exactly. And if you're underwater, the temperature changes less and is less affected by. But there's still the sunlight and photosynthesis and plankton, and the life cycle gets severely disrupted by a huge impact like that. The planetary parade. What is that? What does that mean? What's happening with that?
When you can get your planets all in one part of the sky, then at a certain time of night, you'll be able to go outside and see them all. And so it's a little harder to get Mercury because it goes fast. We catch it for a few days, but the outer planets are all nicely close enough that you can see them spread across the sky, and you can what do you have? You have Mars. We have Mars. We have Jupiter. We have Saturn. For the next few weeks, we'll have them all still. We have Uranus and Neptune. So that's really the idea, is it just so happens at certain times the planets end up being closer together. And that's what we're looking at this spring. If you walk outside, well, there's some planets. And the other thing that's going on this spring that goes along with the planet parade is the eclipse.
Oh, yeah.
And so you have another reason to be outside.
Right.
And when you've seen the moon go red, you can say, now what? And there's some planets I can look at. So the advantage of starting in the early evening looking for planets then evolves to waiting until around midnight for the moon to go into the Earth's shadow. Yeah. And it's going to be spring break week. So everybody goes, well, I'm going to be on vacation. It doesn't matter. As long as you're on the Western Hemisphere, you're going to see it. Now, if you're going to travel over to Bangladesh or India, no, you won't see it. But if you're going to be on our hemisphere, everybody sees a lunar eclipse. They can see the moon.
Right.
Whereas a solar eclipse is very picky. You got to be under the shadow. So it makes the lunar eclipse a kind of very special thing.
It's kind of like when you're taking a group picture and someone says, can the camera see me? I'm like, can you see the camera? Because if you can see the camera can see you. So if you can see the moon, you can see the lunar eclipse.
That's right.
If it's not cloudy.
And so it's something that you could share with somebody who you can't see for some reason or another, and they're 1,000 miles away or whatever. You can both look up and see the same moon, going through the same eclipse at the same time.
Right, and that's so beautiful. I love astronomy. One of my favorite things before, I love my kids, obviously, but they chew up a lot of time, everyone knows.
Yeah.
I used to go out at like 4 in the morning. I had the luxury of being able to, well rested, go out at 4 in the morning, my big 8-inch Dobsonian, and point it at whatever was the hot topic of that time, you know.
Yeah.
And one of the best lunar pictures I ever got, this is off topic, I got in Montrose in 2012 or 2013. Just the most beautiful high resolution, because astrophotography with a Dobsonian is kind of tough. You're pretty limited to...
You need short exposure times.
Short exposure times and, right, so you can't do long exposure that great with a free spinning Dobsonian.
Yeah.
You need a really high quality tracking mount to actually get long exposure of nebula and different
but
dark
the planets
sky
are much brighter, so that helps.
Yes. Now, a good point on that, the planetary parade, things like Neptune and Uranus, even in the best of conditions, are they, let's say you're out in the desert, are they visible to the naked eye?
It wouldn't, you can certainly, on the edge of reality, determine that's Uranus. Okay. Neptune is a telescopic object.
Okay, but it's out there, and if you have a telescope of a decent diameter, I'm sure you could see it.
You don't need to be too impressed.
Yeah. Look at that slightly bluish.
A dot is a dot is a dot.
Orb. Yeah. Exactly. I love seeing stars. The reason I love seeing stars through telescopes isn't because, oh, look at the detail. I can see the spots on that star like you can see on our sun. It's not like, I just like to imagine, I wonder what planets are floating around there. I wonder
what's happening. We do every month. The nearest to the first quarter moon on a Tuesday, when the museum's already open, we're out with telescopes. Now, if it's cloudy, we don't do it, but if it's clear, we're there. And what's most exciting for me is that I would show people something that is gorgeous if you have a telescope and you can integrate light and see it. But when the human eye looks at it, not so much. It's just kind of a hazy, funny little sort of a shape, like the Orion Nebula, for instance. But now we have telescopes that track, but they also integrate, which means they may expose their collector for 2 or 3 seconds, maybe 60 seconds, maybe 1 or 2 minutes, and you see what the computer can see.
Oh, cool.
You see the colors in the Orion Nebula.
Yeah.
You begin to see actual shapes. And it's just a new thing. I guess we've had our first one maybe 10 years, maybe less than that, really. And so we've now up to 3 of these telescopes, and people can have it is definitely the object.
Right.
The telescope is definitely seeing the object. It's not like we stuck a picture in there. This is the object. And you can watch as we integrate over longer time periods, we build up photons on that object to where it's bright enough that your eye can detect color. We can detect shape, no problem, with the rods, but the cones that do color need enough light to do it.
I remember in 2012, again, I lived in Montrose back. I lived kind of close to you. I didn't even know back then. But one of my neighbors came out who he said, I've never seen, he was kind of a doubter of the shape of the earth and things like that.
Dear.
I'm not going to pick any fights or anything like that.
That's okay.
But I was like, dude, I forget what his name was. Come look through this telescope. I got Saturn right here. He's like, Saturn's like, I only ever seen that in a textbook. And I said, come here, dude. And he looked at Saturn and he came back and he was crying. He's like, he was so moved by, he's like, that's up there right now? Like, yeah, move the telescope. It wiggled like, I have to find it again. It's kind of tough to find it again, but that's Saturn real time as far as light traveling from Saturn to us. But that's that dot in the sky. I can show you. This little thing that looks like a star in the sky, that's not a star. I'm pointing at it, that's Saturn. And it was when the rings were more open to us, open face to us, casting a beautiful shadow onto the surface of Saturn. And it blew his mind to tears. And that's why I love sharing. I'm just an amateur, complete amateur astronomer. But if neighbors walk around the neighborhood now, can I see? Oh, Saturn. I only thought it was in a textbook. I've never seen it for real. It's very impressive. Neptune and Uranus. You will take your word for it.
A galaxy can be impressive.
Oh yeah, yes. We don't get me. I'm gonna try to stay on track here, else I can talk for like 2 hours about astronomy stuff. So we covered the possibility of asteroid impact. We've covered the planetary parade, the Mercury capsule.
Isn't that nice?
We got MA2. If you haven't noticed, behind us here, we have MA2. This is it was an unmanned mission, but this space capsule went up February 21st, just like it says on the plaque there, 1961. So we recently celebrated the anniversary of our capsule. So what can you tell us about this capsule and the importance of this capsule?
Well, the fun things about watching people look at it is, first of all, that's not a window. That's the door.
Yeah.
So that was closed in. That's the hatch. That was closed in. There are 2 little bitty windows up that direction.
Right.
You can see one of them. And that's all this astronaut had. Then you look inside and there's a person in there. Now,
a mannequin.
No, it's not a real person in there.
We hope not.
It's amazing how much they thought it was a real person in there. But anyway, he's in there. But you can see the first astronauts weren't very tall. 6'3" and 6'4". Nah, you're not going to pull that one off. So they're smaller men, and that's part of the cause is important because the capsule is so small. The design down at the bottom is the heat shield.
Yep.
And then the way this capsule works when it goes through the air, it will go heat shield first.
When it's making re-entry.
Yes.
Coming back. Yeah.
And so that's critical. This design, you go, well, surely we've gotten so much better. And then you look at the latest capsules like Apollo, and now we're talking about Orion. They still have this capsule you look to them with the heat shield at the bottom, because that guarantees it's not going to roll over on you. And if it does, you're dead.
If it ain't broke, don't fix it.
Yeah. So but the design is the teardrop design. You think about how things go through the air. The teardrop design is the optimal design for not twisting, and so that you can put all of your heat ablation material underneath it, and it'll stay underneath it, and you'll be safe.
Here's what I've always wondered, and maybe you can answer it. Is there a gyroscope in there to keep it pointed where it's supposed to be pointed, or is it all thrusters on re-entry to you got to angle it right before you dive in, or else you're...
I have never looked that up about this capsule. I did, though, for the shuttle, train the astronauts how to set their starfinders, because if they had 3 gyroscopes spinning in the shuttle, and if one of them gets perturbed in any particular way, they don't quite know. They know where they are. They know what's below them. They know their altitude. They don't know their attitude,
right?
The tilt of the ship. And so the gyroscopes were used to get that straightened out. And then if you had to reset a gyroscope, you use the sky. So we designed ways in the planetarium to train the astronauts to look at a pattern from any different direction, how big the pattern would be, and how like they could see the summer triangle. It's about the biggest the pattern could be. Any bigger pattern doesn't help because you can't get it all in the field at once. Things like the Pleiades were wonderful. And so, but the way the star trackers were done is that you got close, the star tracker got it. And then it could use that to know how to reorient the gyroscope to know how the spacecraft was tilted. And of course, that becomes critical when you're re-entering. You like to be able to know which side's going down first for your heat shield problems.
Right.
But in general, if they wanted to point a piece of equipment, if they wanted to do anything that required them knowing exactly how they were tilted, they had to rely on the stars and the gyroscopes. Now, the Hemberger Planetarium was the second planetarium in the U.S. to train astronauts. The first ones, the Apollo ones, were trained in North Carolina. But we got the ones, all the shuttle astronauts were trained in our planetarium.
That's amazing.
And we had a whole program, and we could still bring pieces of it where we could put the shape of the shuttle in the cockpit windows, and you could then see what was moving by and see if you could name it. So we've always had fun with it. It makes the planetarium special.
Yeah. The planetarium is very close to our hearts.
Yes.
This smell, I've been holding this, and I can smell the iron. Like it's wafted up to my nose. It smells like an old car or something. It's
or blood.
Or blood, dude. Yeah, I was like, dude, are my teeth bleeding? I have recently had my wisdom teeth out a couple weeks ago. I can talk now, but am I tasting blood? It was this meteorite. That's so cool.
Yeah, the iron in your blood is one of the oldest things on Earth.
Yeah, and isn't it formed inside of a supernova or inside of the core of a star?
Chances are it could be traced back if one did that kind of thing. But one could trace back the iron on the Earth that all the way back to the supernova that caused the formation of the solar system, that produced the materials that ended up becoming part of the solar system. So iron is a very old thing, and you're carrying it around with you.
I've wondered that until recently. I get to work here and learn all sorts of cool things. How did our sun form? How did our sun ignite? That the going theory now is that we were a big ball of mostly hydrogen gas and plasma or whatever. Plasma happens with condensed gas and it emits light and all that stuff. But anyways, it was a nearby supernova. And that shock wave.
It was the pressure wave, yeah.
That pressure wave from that nearby supernova condensed that cloud and sparked the fusion inside of that cloud, in which that's where you create all the heavy elements and the photons that reach Earth.
We had to coalesce, and it gave us a central body to coalesce around. And then, given enough time, and balls started appearing, and they started collecting more material and cleaning up the solar system. That's why we have a few asteroids, and a few comets, so we don't have a lot of them because the planets have cleaned them out.
Right.
Over time.
A very loose, and I mean extremely loose analogy is you got a dusty floor and you dust it all into your bin. Oh, now it's collected into a more central location.
Right.
And it kind of, since there's no gravity out there, well, it's not affected by, it coalesces it more or less into a ball. There's a central point, and since the gravity is all directions, it kind of more or less collects into a ball.
And see, we knew this wasn't a ball as such, it was more a disk.
Right, the disk.
Because the planets are in a disk.
Right, but I'm saying the moon and the Earth, they settle on the shape of a ball. It was a disk, of course, after in the protoplanetary disk and everything like that. But eventually, as things get swept up and coalesce, they all kind of form more or less a ball shape. Although the Earth is more
an object that most asteroids are not round. So one of the working on definitions. One of the definitions of a planet, trying to decide whether Pluto got to be one or not, and the result was no. But the planet, it's got to be a round object. Pluto is a round object. It's big enough for that. Ceres is a round object, which is an asteroid. But it has to have cleaned out its orbit. And so they played around with it enough to get Pluto kicked off. Because basically we have a lot of little Plutoids floating around. In fact, I wish they call them planetoids. I wish they'd called them Plutoids. and they're in the outer solar system. But they didn't, because they're so different from everything else that's a planet, that now there may be another planet, but it's going to be so far away, still orbiting the sun, but so far away that we can't see it normally, and the area where we would expect it to be is in the Milky Way. So the background upon which it's in front of makes it even more unlikely to find it.
I mean, I guess one way it is so far beyond my pay grade to even conceptualize this, but I like, one of the ways that we theorized black holes' existence was, well, we may not be able to see it directly, but we can see how it affects things around it.
If a thing that we can see, a planet we can see, is orbiting something we can't see, we can tell by the behavior of the planet how much mass the thing we can't see has.
Right.
And if that mass is teetering around 8 or 9 or even down to 6 or 5, that's there, and we can determine, we can pretty much say we can't see it. It's small enough. It's probably a black hole.
And we have since directly photographed black holes. We have confirmed.
It took
black holes
telescopes
exist
all around the Earth, all looking at the object at the same time.
In the middle of MA, 83. It's a Messier object that, as I understand, the first one that they aimed all the hundreds of telescopes around the Earth on, MA83.
I'm not sure about that one.
I'm thinking MA2 because of the capsule. Whatever. It was it's in the center of a galaxy far, far away, and they were able to I see the disk,
M87.
the accretion disk, M87. See the accretion disk around it, and it looks, when you see the photograph, it looks like an unimpressive orange blob around a black hole.
It's the fact that we can see it.
Exactly.
And in fact, it matches what we thought we would see is, I think, even more impressive.
Yes.
That's why we do shows on black holes. It's fascinating that as projectors get older, they can't project black as well. You think, well, black's got to be easy. It's nothing.
Yeah,
but
right.
actually, a projector makes things grayer. If you look at an old projector you may have,
right,
it's getting grayer and grayer and grayer. You go, that doesn't make sense, but it actually does. When you go in the planetarium, you want the sky behind the stars to be velvet black. When you buy a TV, you want the contrast, the vividness of the image is how well the projector projects black.
Or doesn't.
Or doesn't.
Or doesn't. That's the thing with OLED. I'm glad you brought up the OLED TVs, because that's why OLED currently, as a recording, is one of the best display technologies. It's because the pixels that are black, they just aren't on. They're not emitting any light. So black is black on an OLED TV versus an LCD or something always has the backlight projecting through, pushing through a pixel. So that's why when you watch old Star Trek Next Generation or whatever, and it's it's kind of gray back there. That's just the technology of the TV. The dark sky is increasingly vanishing, unfortunately, due to human progress of humans expanding and moving out to south of the city and everything like that.
We like our light too.
Exactly. I want to see where I'm going when I'm driving. I would like to see, taking the trash out to the street. Totally, but if someone watching this or listening to this lives out in the desert or something, I hope they cherish the jewel that they have, that they can go out into their backyard or whatever and look up and see the clouds of the Milky Way. That's something we take for granted. I couldn't see that in Montrose. I can't see that where I live in Missouri City. I can see some stars out there.
But it's there, yeah.
Right.
We want people who come here to see what the cities have lost.
Right.
What's still real, what's still our legacy, but we can at least capture it, make it feel like it's like you're really there, make the room go dark and the stars explode overhead. It's just gorgeous. But you have to be able to do black, which I always thought was fascinating.
Right. Well, we want to see stuff. No, black, that's the other side of the coin to seeing things is...
They got it. If the background is too... You don't see anything now in the city because we have too much urban light. So it's not that the object has gotten fainter. It's that the background has gotten brighter. And so that's what you fight in trying to make the most realistic and wonderful experience in a planetarium. Make it feel like you're really there, which means make it dark.
Yeah. Maybe we should put some coyotes outside so they can hear coyotes.
We could do that too. We could pipe that in.
Some sound effects. Carolyn, what should people do this spring break? Where should they go this spring break?
There's lots of things they can do. The number one thing they should do is come to the museum, because we have a lot of probably new to them exhibits, new things to explore with kids. So we'll have the dark sky, I promised.
That's very great. I think we've covered everything. Dr. Carolyn, thank you so much for joining us today.
Thank you.
Good.
Thank you for listening to the HMNS Beyond Bones podcast. If you are listening to the audio-only version, be sure to check the description for show notes clarifying any areas of confusion you may have heard. You can also check out the video version as well on YouTube for instant on-screen clarification and, of course, other visual aids. We'd also be honored if you'd consider sharing our content with your friends and family. But with that, as always, I'm your mental curator, Johnny Hemberger, reminding you to stay safe, stay curious, and come out and visit us at the Houston Museum of Natural Science.